Okay, good morning, Sir Jess. I may apology for the late upload because of royal cable, but let's continue. So, let's start. My name is Lian Justin Salundaga, and my group mates are Kristen Joy Pelicano and Chelsea Mike Viado. No? However, due to slow internet connection, we cannot record our presentation live. So, I've told them that they submit a certain audio recording that would explain each slide, no, so we can still continue not to pass this. So our study, if you remember, in the past proposal defense, we have already discussed our membrane is not just limited to microbial fuel cell, and we already know that proton exchange membrane can be also applied to desalination plants, wastewater treatment plants, and etc. No? So membranes are commonly used in different types of industries, especially in renewable energy technologies. And one of the most novel renewable energy technology is a microbial fuel cell. But what's the problem with microbial fuel cell? It looks like a laboratory scale. Yes, it's still in laboratory scale, no? And what hinders this microbial fuel cell in a larger scale production is the cost of the membrane. Actually, the cost of the membrane that is commonly used in a microbial fuel cell costs thousands of dollars per just 30 centimeters. So imagine, you have a 30 centimeter or a meter of enough ion membrane, but it will already cost thousands or ten thousands dollars. What if we are going to expand this fuel cell into a larger scale production? What do you think? Are there still a person that would still invest on that high amount of capital costs? Hmm, no, di ba? Because enough ion membranes are also susceptible to biofouling and chemical degradation. Now, mahal na, lugi ka pa. 'Di ba? Are you going to invest on that? So what are we trying to prove? We are going to prove and to provide an inorganic material that would serve as an alternative to that high cost membrane. No? So let's go back. Let's rewind our introduction. No? So background of the study. No? So we already know that there is a continuous rise in energy demand, right? Ay, you already hear that on many groups, no? Fossil fuels are depleting. Hmm? Repeatedly, students are repeatedly saying the statement that fossil fuels are depleting. Non-renewable energy sources meet 90% of the world's energy. Medyo nakakaumay na, no? But look at the price of petroleum today. It is already nearly 70 pesos. But 3 months before I presented this paper last term, no, I've already said to you that the consequences of our own actions, no, will make us suffer in the future, no. And this is the future. Imagine an increase in the price of petroleum just because of a tension in Ukraine and Russia, no? As days pass by, as years pass by, we are going to feel the drastic and absolute changes of our decisions that we make today, no? Because pasok sa kaliwang tenga, labas sa kabilang tenga. We are not doing anything, Yes, we make study, but do you think the government invest on this kind of no, the government will only focus on the problem if the people of the state already feels it, no. But now the price, before pandemic, the price of tricycle is just 9 pesos from Asa to Pulo. But now it's already 90 pesos. Imagine, it's just a matter of it's just a couple of months or days. It's 90 pesos already. See? See? No? We are going to face that imminent changes in the future pa. No? If we do not make certain actions on the fossil fuels, we cannot achieve anything. That's why we are trying to invest on the renewable energy technologies. No? We try our best to facilitate the use of these renewable energy technologies that is not only limited to the solar energy. There is wind energy, there is geothermal energy, there is hydro, they call that the dams, the energy in the dams, no? But but we already know that wastewater is also abundant in our places. So if wastewater is abundant, and there is and it is proven that it can we can possibly harness electrical energy from that, what are we going to do? See, diba? We have to utilize that waste into energy, and that's what makes microbial fuel cell unique. While treating wastewater, we are producing electricity, no? So in a laboratory scale, but no, there are lot what hinders microbial fuel cell in a larger scale, the high cost membranes. So what are we trying to prove here? We are going to evaluate the performance of that microbial fuel cell using an alternative membrane from dihydrogen phyllosilicate and activated carbon from coconut shell. No? So later we are going to discuss what the hydrogen phyllosilicate is, but our specific objectives are already listed here. And our last objective here is the measure the coulombic efficiency of this microbial fuel cell. However, because of certain conditions of our microalgae and availability of laboratory to test the COD determination in a matter of days, but it would take 2 weeks just to give us the results for the COD. We cannot still compute for today the Coulombic efficiency. But these eight objectives are we have already achieved this. No, so later we are going to discuss that one by one. No? So let's hear Tin.
As a proposal, in order to fill the gap that limits the development of microbial fuel cell and impedes one of its application in the higher scale, a membrane that is made of activated carbon derived from coconut shell is proposed as an alternative. Since the price of 1 kilogram of activated carbon derived from coconut shell is approximately 200 pesos or 1.97 US dollars per square meter. Furthermore, according to NITU, ACCS or clay membrane showed higher proton diffusion coefficient with 36 times 10 raised to negative 6 square centimeter per second than NaF-ion 117 membrane with 4.64 times 10 raised to negative 6 square centimeter per second. Study of NITU shows the performance of microbial fuel cell and evaluated using this membrane, which showed ACCS clay membrane-based microbial fuel cell exhibited 1.5 times higher operating voltage and coulombic efficiency with 2 times higher power density as compared to microbial fuel cell using NaF-ion 117 membrane. Thus, low-cost PEM or proton exchange membrane has the potential to make microbial fuel cell technology step forward for field-scale application by eradicating the need of costly polymer membrane popularly used at present.
So thank you, Miss Chelsea. So just like what Miss Chelsea said, no, the step forward, no, in eradicating the eh, in implementing microbial fuels and in a larger scale production is one step forward is the finding an inorganic ceramic membrane. Because inorganic ceramic membrane, just like bentonite, kaolinite, they are found, there are minerals found in the mountains, in etc. No? So if inorganic ceramic membrane is more abundant than polymeric membranes, basically inorganic ceramic membranes would cost lower than the polymeric membranes, right? Because polymeric membranes are often synthesized, no? And they are all artificial, no? That's why the cost of a polymeric membrane is much higher than the inorganic ceramic membrane. But they are both susceptible to biofouling, but the difference is the inorganic ceramic membranes are more efficient in terms of cost. No? So let's continue. Just like what we have said, the conceptual framework, no? Our input would be this would become the anode, and our cathode would become the microalgae, no? So if we use a living organism as a cathode, it is called biocathode. And we have a dihydrogen phyllosilicate clay, and the process is casting the acyclous membrane, the biomass production of the cathode while inoculating, and the microbial fuel cell construction and operation. Siyempre data gathering, no? Output is siyempre data about the voltage, the proton mass transfer coefficient, and the swelling degree. So what is this swelling degree tells us, no? When you say swelling degrees, how something swells, no? Is it good or not, no? So later we are going to discuss the data that we have gathered if a swelling degree is good or bad from an ion exchange membrane, no? So here we are going to discuss the method of fabrication of the ceramic membrane. So first of all, if in order for us to create a fuel cell, you are first going to fabricate the ceramic membrane. And these steps are listed here. So we are going to establish our knowledge here one by one later. So
Kaolin is a major component for the ceramics industry. Its high fusion temperature and white firing characteristics make it particularly suitable for the manufacture of traditional ceramics such as sanitary ware, tableware, wall and floor tiles. The kaolin powder with mineral kaolinite is a cosmetic clay used in cold process soap, bath bombs, and masks. This grade is a pure natural mineral anhydrous aluminum silicate composed of kaolinite with low iron content. This clay can be used on normal, dry, and sensitive skin because it does not throw oils from the skin. It is also very mild clay that works as thickening agent.
so this is what Miss Pelicano pertains to, no, the commercialized kaolin clay, no? So commercialized kaolin clay is used basically in face mask. The face mask for skin exfoliation, they call that, just like that, no? So the kaolin clay that we use is 500 gram of kaolin clay. We bought 1 kilogram of kaolin clay, eh, and we purchased that commercially. So this is commercially available, no? So the first step in kaolin clay, it will not it is impossible to make kaolin clay a membrane if it is just a kaolin, no? Why? Because we need to transform that kaolin into metakaolinite. And the only thing that the only process that we can consider to transform kaolin to metakaolinite is the thermal dehydroxylation. So meaning to say, later Tin Sanchez would explain that, no? What is thermal dehydroxylation?
Literature has shown that thermal degradation of raw kaolinite clay results in dehydroxylation with steady increase in the distillation of its tetrahedral silicate minerals or SiO4, thus giving rise to crystallization of the inert phase of the material with a major effect on its reaction chemistry. Dehydroxylation is the reaction of decomposition of kaolinite crystals to a partially disordered structure. This change is followed with a smaller shrinkage of the dimensions of the sample and the porosity rise.
So what so Miss Pelicano said, no, she explained that the thermal dehydroxylation is basically uh, the transformation giving rise to the porosity of kaolin clay, because originally the structure of kaolin clay is just here, no? So we cannot achieve anything here. But because of dehydroxylation, we are going to dehydrate this one by removing a water molecule. So removing a water molecule from inside of the kaolin membrane would give us a porosity rise, no? So we give us a hole that is larger than the previous ones, no? So and here, what we have done in our experiment is that this kaolin clay is subjected to oven for 2 hours in a 300 degrees Celsius, no? So 300 degrees Celsius is the optimum temperature for thermal dehydroxylation according to the study of Nitu, no? So this kaolin clay subjected to thermal dehydroxylation for us to use it as a membrane, no? Because simple kaolin clay would not give us anything, no? Because it is still not a metakaolinite. The main difference between metakaolinite and kaolin is the structure, no? And what are we going to harness in the membrane is a metakaolinite structure. This is this one.
Literature has shown that
I
About
prolonged degradation of raw
150
kaolinite clay
sorry,
results in
I haven't paused.
dehydroxylation with steady increase in the distillation of its tetrahedral
I haven't paused Miss Pelicano yet. No, wait. Sorry for the inconvenience.
about
So, at the start of experiment here is Miss Viado, no, to explain the next step of thermal dehydroxylation, which is the mixing and addition of absorbent.
For the initial characterization of the separator, clay was mixed with ACCS in different proportions of dry weight, namely 1%, 2%, 5%, and 10%, with clay being the
So, Miss Pelicano tells us, no, that the mixing of 1% activated carbon and clay, 2% activated carbon clay, 5% activated carbon clay, 10% activated carbon clay. So what do we mean by that? Meaning to say, if we have 100 grams of activate if kaolin clay, there is 1% activated carbon on that. So what is the best proportion of activated carbon and kaolin clay that would give us the highest proton mass transfer coefficient, no? Because higher proton mass transfer coefficient is related to the voltage output, no? Because a higher proton mass transfer coefficient is directly proportional to the voltage output according to the studies, no? So in here,
About 150 grams of kaolinite clay sample obtained was subjected to thermal dehydroxylation process. Moderate thermal treatment of kaolinite affects its cation exchange capacity and further enhances its stabilization properties.
so here in the mixing and addition of adsorbent, the one we use here is already, according to Miss Chelsea, it's already thermally dehydroxylated, no? So we are going to mix, and the addition of sorbent meaning we are going to mix the activated carbon, because activated carbon is the sorbent, and the pore forming agent, which is the uh, starch, no, or the polymer starch, no. And why do we add a pore forming agent? Kaolin clay is not enough, no, to provide kaolin clay, metakaolinite has a large pores. However, the addition of activated carbon would block that pores. So what are we going to do? We're going to use a pore forming agent to create more pores, no? Because we are trying to add an activated carbon because it is already proven, no, that the use of an activated carbon would increase the efficiency of that membrane, no, to transfer protons in with the aid of the process, the Grotus mechanism, no. So PFAC is an additive in the integrated microbial fuel cell to mitigate the membrane fouling. So that's what are we trying to prevent, no? That the membrane fouling, no? And as a result, according to other study, increase as a result, the addition of activated carbon on the ceramic membrane increase the membrane flux because of scoring action. So some studies were focused on the coupling membrane treatment with powdered activated carbon. It is our study, no? So what is the ratio of kaolin and a activated carbon? The best ratio that would give the highest amount of proton mass transfer coefficient. In order for us to do that, in order for us to get an accurate result, we use three replicates and we average that. We use three replicates again and we average that. This is for the trial. This is for the trial one. The trial one is a 1% activated carbon. Trial 2 is 5 2% activated carbon. Trial 3 is 5% activated carbon and so forth. So as you can see, the mass of container is first measured, which is the paper box. And in order for us to get an accurate measurement, no, this paper box is measured, the container is also measured. In order for us to get the final mass of the sample of the kaolin clay, is we subtract the mass of the container of the sample to the mass of the container, no, because this is weighing by difference, no, in order for us to get a more accurate result for the first replicate. And the average of that is the final mass of the sample for the trial one, no, analytical chem. Next, same in activated carbon. We first measure the mass of the container, then we measure the mass of the container with the sample, and we measure the final mass of the sample by subtracting the mass of the container plus the sample minus the container. So that's all. So next step from mixing and addition of adsorbent is this one, no? So in our study, the addition of adsorbent or pore forming agent is very important, no, for us to utilize the kaolinite clay, no, because kaolinite clay is our main material, no. So just like what I have said, an addition of activated carbon would increase is a, would increase the effectivity of that membrane to become substitute to naphthion because of its resistance to biofouling. Now, so we are going to investigate that later, but our focus is Coulombic efficiency, the voltage produced by that membrane. No? So we homogeneously in a 250 ml beaker, we mix the activated carbon and the kaolin clay measured. No? And later, we add the sodium alginate solution, which we will discuss later. We add the sodium alginate solution for us to have a stronger polymeric structure. No? So later, we are going to discuss that. Okay.
Manihat starch clay composite is a modified variant selected to function as a proton exchange membrane or PEM. The choice of starch was based on the presence of strong intermolecular and intramolecular glycosidic hydrogen bonds in its polymer chain. Hence, incorporating starch in the hybrid improves the strength, hydrostatic stability, and proton conductivity of the base substance, which is clay. About 5 grams of sodium alginate powder in a suspension was added to increase the bonding strength of the starch clay mixture.
So here, uh, it's like what Miss Biado said, that the starch here is a would increase the performance of that membrane. Sorry, we so sodium alginate is used as a binder, no, to increase the performance of that membrane. So this how we utilize that the sodium alginate that we bought from DKL Laboratories. No, so it costs 670 pesos for just a. It costs already 600 pesos for just a 25 grams. So we add 5 grams of sodium alginate and we increase the stirring so it would melt in water. So if you remember, our binding agent is polymer starch and our forming agent is a pen. Let's continue.
The mixture was thereafter charged into a 0.0127 meter diameter pipe of length 0.08 meter and allowed to cool. Each of these parameters was varied in order to satisfy the requirements for CCD study.
So we have subjected the membrane into in a coupling and a pipe, no, so the size of the pipe is 0.0017 meter diameter. So after we mold the mixed sodium alginate, the mixed starch with activated carbon and kaolin clay, we are now going to subject this one to another type of process, which is the air drying. So we air dry this one in 5 days to remove the moisture from it. Now to further test the it has no moisture inside, no, we oven this for just 100 degrees Celsius for just a 15 minutes until constant weight, no. So the membrane that we have used is a 5 millimeter thickness, and we are now ready on the next step, which is the thermal sintering and firing. So when you say thermal sintering is important because it is heat treatment commonly used to increase the strength and structural integrity, no, of a given material. So in powder metallurgy processes use sintering to convert metal and powders into unique materials into end use. Now, sintering is also called a firing or frittage. So it is the process of forming a solid mass of a material to heat and pressure. That's why our membrane that is subjected in an oven by uh, is sintered, no, and fire or sintered or fired in an increasing temperature. So when we say if we would heat this one, we will not start if, for example, the temp is 270, we will not start at 270. We would start at the we will not start at 270, but we would start at the bottom, which is 50 degrees Celsius, and we will continuously increase that every 2 minutes in an oven. So that's it. This is direct firing, but we also do here for the membranes that cracked here. We repeat that now with the same thickness, with the same sizes. So the fuel cell fabrication includes the use of the epoxy. No, so the membrane separator surface area is about 55 centimeters squared, and as a fixed acrylic sheets with epoxy-based adhesive to separate the anodic and the cathodic chamber in order to maintain the anaerobicity of the anode chamber. So here are we have done the fuel cell fabrication. And next step is the proton conductivity experiment. No, so after creating the fuel cell, we are now in the you're going to use this one, no? The proton conductivity to measure the proton mass transfer coefficient. When we say proton mass transfer coefficient, this is the amount of proton that transfers from the anode to the cathode. But first, we first calibrate the pH, no? For us to obtain an accurate measurement, no? So this is the process how we have done that. This is the anode chamber, this is the cathode chamber. So basically, in theory, the protons in anode chamber will go to the cathode chamber because this is a proton exchange membrane, no? Now, in order for us to do that, we are going to measure initially the pH of this one in 200, and we will monitor that in 120 minutes. Later, we are going to show the data for that, no? And the data for that is here in a table here, no? So as we could see in the trial 2, we have seen in the trial 2 that we start in a pH of 6 point, wait lang. We have started 6.95. And the graph says here that it has, the anode chamber is blue one. It has a positive slope. So basically, if we have a positive slope, no, the trend of pH here would increase because of the decrease in protons. So basically, what happens is that the protons here from the anode chamber is transferred from 2 minutes to 120 minutes to the cathode chamber that becomes 9.86. But what happened to the cathode chamber? Since on the trend, on the trial 2%, we obtain a negative R value, meaning to say if you have negative R value, you have a negative slope, meaning the trend is decreasing, no? But it is slowly decreasing, no? So if we were going to uh, uh, try to find the initial pH of the cathode chamber, it is 10.48, and the resulting is 9.86. So it decreased slowly, no? But it the proton is transferring the proton that we have monitored is increasing, no? If you could see, the first line is more precise than this line, no? The precision of this is the operating line, but the points is higher, no? So yun. So next, we also tried the trial 5 or trial 3 for the 5% activated carbon. And the 5% activated carbon, we have measured 6.94 for the first 2 minutes, but the final time by the final pH is 9.15. So if we can see in the trend on the graph, it is slowly increasing, no? Actually, it is going to straight line if it goes to 5%. But the slope is still negative, so the cathode chamber has a decreasing value of pH. So meaning to say the proton is being transferred here from the anode. No, that's why the anode's pH is getting increased because of the increase in hydroxide ions or the decrease in the proton ions. No, just the graph. And for the trial 1%, we didn't put this in PPT because this is very high. This very large data. We have measured 6.99, but the final pH after 120 minutes is just 7.15. However, if you could see at the graph, it's just like a constant, no? So it is different from 2%, and it is also different from a 5%. So later, we are going to discuss what's the difference that comes between the trial 1 and the trial 2. And the trial 1 with 1% activated carbon, and the trial 2 with a trend of this one, no? It's more increasing, no, than this one. And lastly, we have also tested the 10%, which is the trial 4 that has a 6.98 and the initial pH and the final pH of 7.18. It's much larger than the first one, but the final pH from 10.60 it just becomes 10.48. So it decreased by 0.12 8.12 only, no? But if you can see the slope is still negative, so therefore we are on the right track, no? And the slope for the anode chamber is still positive, so therefore the protons are increasing. So we have also noted the mass and protons membrane, the mass of the proton exchange membranes that we have used, which is the trial one, which is this one. We take the average. Here is the mass of the sample, and this is just the ratio. Now, in the swelling degree, we have seen that the swelling degree of this one of trial 1% is just 7.44, but the trial 2% is 23.79, the trial 3% is 17.59, the trial 4%, which is 28.96. Actually, the swelling degree would tell us the higher the swelling degree, the lesser the higher the swelling degree would give a more inefficient proton exchange membrane. So basically, actually, a higher swelling degree of that membrane, basically protons only would pass on that, no, not water, no. So if it is a high swelling degree, there is a problem on that membrane, no. And one of these is the ratio of activated carbon and kaolin clay, no. So that's all for our first study, because uh our cathode chamber is still in the process of inoculation for 30 days, no. So what happens in Iloilo is that they have delivered this late. So what happens is that the Chlorella sorokiniana initially died, no, in just a matter of 20 days, no, because in a microalgae there is a lag phase, eh. This will exponentially increase, but actually it will reach the stationary phase until the culture goes to zero, no. So yun. So what happens is that they deliver the in Iloilo, they deliver the microalgae we ordered in Iloilo in the stationary phase. So basically the culture went down here because of the delayed in flight. So what we're going to do, we're going to order again, no, Chlorella sorokiniana, and it's in this the process of inoculation of the cathode chamber. And our last data is the Coulombic efficiency. That's the last data we have. So basically, if we have 9 objectives, we have already finished the 8 of that objectives, but the last objectives, which is the Coulombic efficiency, we have still not yet done. So that's all for our presentation. Thank you very much for